Part 2 of Lesson 5, Chapter 2 is again on rational functions, and here's some notes for you to take down. So if you can take out a piece of paper, these will help you understand the different parts of rational functions. First of all, anytime you're asked to find vertical asymptotes, set the denominator equal to 0. Vertical asymptotes, set the denominator equal to 0. To find x-intercepts, set the numerator equal to 0. Okay, set the numerator equal to 0. And then for y-intercepts, put 0 in for all x's and then lastly the horizontal asymptote, it's going to be kind of conditional, if you will. It can be one of three conditions. You're going to have to look at the degree of the numerator and the denominator. And if the degree of the top is less than the bottom, then it's y equals 0. Just a horizontal asymptote right on the x-axis. If the degree of the top is equal to the bottom, then you have to divide the leading coefficient. And I think I showed you some examples of that yesterday. And then here's what's new, is if the degree of the top is greater than the bottom, then you've got a slant asymptote. And I'm going to show you how we find that today. So there's your notes. Alright, so a slant asymptote, or in other words an oblique asymptote, is when it's not going horizontally but it's going at an angle, as you can see in this one. What's going to be true, every rational function that has the degree of the top larger than the degree of the bottom. So you can see in this example we've got an x squared on top, we've got an x to the first on the bottom, therefore we've got a slant asymptote, and I'm going to show you how we find that slant asymptote. It's also called an oblique asymptote. So here's an example. You can see the function that they give us, 2x to the third on the top, x squared plus x minus 12 on the bottom. You can see it graphed. There is no horizontal. There is a slant or oblique asymptote. The directions say determine any asymptotes and intercepts for this function. So let's first figure out the vertical asymptotes by factoring the denominator. We got x plus 4 and x minus 3, which means that we'd have vertical asymptotes, two of them, one of them at -4, the other one at +3. Hopefully you can see that in the graph there. Now to find the slant asymptote, what you have to do is you actually have to divide the two polynomials. So we have to use long division for this. Now it's not going to be very hard. I'm going to put in a 0x squared, a 0x, and a 0. And so now I type a 2x up here. 2x times each of these would give us 2x to the third, 2x squared minus 24x. Subtract the bottom values from the top, and we're going to get a -2x squared plus 24x, and then bring down the next term of 0. Do this one more time, and we'll have to have a -2 right here, and that should give us something like that. Subtract the bottom values from the top, and we end up getting that becomes a 26x minus 24. Now, what's left over here at the bottom, this is the remainder. We don't care about that for the oblique asymptote. We've just found our oblique asymptote right here. So I'm going to say my slant asymptote is y equals 2x minus 2. Okay, so that's how you find your slant asymptote. And you can see this diagonal line is y equals 2x minus 2. What else do we need to find here? We need to find intercepts. So to find an x-intercept, you set the top equal to 0, and that's just going to give us 0, 0. And to find your y-intercept, put 0 in for all the x's, and that gives you the same thing, 0, 0. So we only have one intercept, and it is both an x and a y-intercept. And then lastly, state the domain. The domain is going to be all numbers except the two numbers that we have vertical asymptotes at. So negative infinity to negative 4, unioned with negative 4 to 3, unioned with 3 to infinity. That's basically all numbers except for negative 4 and 3. So last thing to discuss on part 2 here is some graphs have what we call holes. Okay, a hole can be found when there's a common factor in your numerator and your denominator. If you take a look right here, I know there's not numbers there, but if you had an x minus a on the top and an x minus a on the bottom, you could cancel those out, then you'd end up having a hole at a. Okay, and you can see that here in the example. So here's one that has a hole in it. You can see the hole is located right here. I want to show you guys how to find that. Okay, so they give us the function. The first thing I'd want to do is I'd want to factor the top and the bottom. So the bottom factors into x minus 4, x plus 2, and the top factors into x minus 2, x plus 2. So hopefully you can see that there's a common factor, the x plus 2's, so there's going to be a hole at negative 2 comma something. Now to find the corresponding y value right here, what we have to do now is take this x value of negative 2, put it into the rest of the function, not the part that I canceled out, but if I put it into the rest of the function, we'd end up with, let's see here, negative 4 on top and negative 6 on bottom, so that reduces into positive 2/3. So our hole is located at negative 2 comma 2/3. Now it asks for other parts, so vertical asymptotes, horizontal asymptotes, so let's list those out. You've got your notes that can help you. There's only going to be one vertical asymptote. It's going to be at x equals 4, not at negative 2, because there's a hole at negative 2. Okay, we've got a horizontal asymptote. Now the degree of the top and the bottom is the same. It's x squared on top, x squared on bottom. Therefore we divide the leading coefficients. 1 divided by 1 gives us y equals 1 for your horizontal asymptote. Hole, we've already listed that. Intercepts. Set the top equal to 0 and we'd get, let's see here, plus or minus 2, positive 2, yeah. So we have an x-intercept at positive 2. We don't have one at negative 2 because that's where we have a hole. And then we also have a y-intercept by putting zeros in for all the x's. We have a y-intercept at negative 4 over negative 8, which is 1/2. So we have two intercepts, and state its domain. Its domain would be all numbers except where the vertical asymptote is and the hole. So negative infinity to negative 2, unioned with negative 2 to 4, unioned with 4 to infinity. That would be your domain. Okay, one more example, same kind of problem. So you can see they gave us a rational function. Let's start off by finding the holes by first factoring the top and the bottom. The bottom factors into x plus 4, x minus 3. The top factors into x plus 4 and x plus 6. So you can see we've got a common factor on top, the x plus 4's. So we're going to have a hole at negative 4 comma something. How do we find the corresponding y value right here? We take the -4, put it into the rest of the function. So that would give us, what, a 2 on top and a -7 on bottom. So -2/7 is the y value of the whole. And now to find the rest of the parts, the vertical asymptotes, there's only one of them, x equals 3. Horizontal asymptote, let's see, we've got x squared on top, x squared on bottom, so divide the leading coefficients. 1 divided by 1 gives us 1. And we've already listed our whole. Our intercepts, let's see here, if we put 0 in for all the x's, we're going to end up with 24 over -12, which is equal to a -2, so we should have a y-intercept at -2. And if we set the top equal to 0, we get an x-intercept at -6. So we have 2 intercepts. And then to state its domain, domain would be all numbers except for the vertical asymptote and the whole. So from -∞ to -4, -4 to 3, and then from 3 to infinity would be your domain. Here is part 2 homework problems, number 15, and then 21 through 29 odd. You know what I forgot to do? I forgot to come back here and graph this. So I just want to show you guys. I've got it typed into my graphing calculator, and now when I graph it, we should see something similar to what we just got done talking about. If I toggle back and forth here, you can see on this problem, we said there should be a vertical asymptote at 3. Let me put that in right here. Does it appear to be flattening out there at 3? It does. We also said there's a horizontal asymptote at y equals 1. Does it appear to be flattening out at a height of 1? It does. We have a y-intercept at -2, so if I press trace and type in 0, we should see the y-intercept at -2. That confirms it. We also saw an x-intercept at -6. So if I type in -6, it confirms that we have a y-intercept at -6. We also have a whole at -4. So here's how we test that. Type in -4, and notice right down here, there's no output. That means that 1, 2, 3, -4, even though the calculator doesn't show it right here, there's like a hole, an empty circle right there in the graph. So that's how you can use your graphing calculator to assist you. Here's the homework problems for part 2.